Okay, so now let's go ahead and try to solve our radial Schrödinger equation, which was our simple toy model for the hydrogen atom. It's also called the particle in a box. So remember, this is what we said. We said that we can model a hydrogen atom, the state of an electron. We can model the electron in a hydrogen atom as a particle which is confined to a one dimension, this radial dimension where it's sitting on a segment of some length L. We've understood how to describe the state of such a particle on a line. We understand what the Hamiltonian for a free particle looks like. Now let's try to understand the energy eigenstate so we understand how the state of this particle evolves in time. So let's go back. So let's see how, there are two ways we can represent Schrödinger's equation once we confine the particle to being between 0 and L. One way we can do it is we can say there's an infinite potential as soon as you go beyond L that prevents the particle from going there. So what you would say there is that if you write down Schrödinger's equation, which looks like this, IH bar d psi by dt is H psi, then H would consist of the kinetic term, which is p hat squared over 2m, as we saw before, and then there would be this potential term, which would be 0 inside this segment and infinite outside. Okay, or we can just say, since the particle can never be in this interval between 0 and minus infinity or between L and plus infinity, we'll just impose boundary conditions saying that psi at 0 equal to psi at L equal to 0. And then we'll just keep the kinetic term around. And that's a simpler way of doing things. So that's what we'll do. So we'll drop the potential energy and we'll just say IH bar d psi by dt is minus H bar squared over 2m d squared by dx squared of psi with the boundary conditions psi of 0 equal to psi of L equal to 0. Okay, so now we want to solve this Schrödinger's equation. How do we do this? Well, remember what we do is solving Schrödinger's equation is easy once we figure out the eigenvectors and eigenvalues of the Hamiltonian. So that's what we want to do. So we take our Hamiltonian H, which is minus H bar squared over 2m d squared by dx squared, and we want to figure out what are the eigenvectors and eigenvalues of this Hamiltonian. Okay, so let's figure out what's an eigenstate of this operator. And just by looking at the structure, we're going to guess that the eigenstate is of the form e to the I kx. Right? Because when we look at h times psi of x, this is minus h bar squared over 2m d squared by dx squared of e to the I kx. And when you differentiate twice, you get minus h bar squared over 2m, and you get I times k whole squared e to the I kx. I squared is minus 1, so you get h bar squared k squared over 2m e to the I kx. Which means that the eigenvalue, which is the energy of this corresponding eigenstate, so let's call it E times e to the I kx, E sub k, it's the energy corresponding to this eigenstate e to the I kx. This tells us that E sub k is h bar squared k squared over 2m. Okay, now this immediately tells us that these eigenstates come in pairs, that e to the I kx and e to the minus I kx have the same energy. And that also tells us that any linear combination of them has the same energy. So we have solutions psi of x, which is of the form a times e to the I kx plus b times e to the minus ikx. And both of these, and this has energy E sub k, which we already wrote up here. Okay, so now in order to figure out these eigenstates, we also need to impose the boundary conditions. And in order to do the boundary conditions, it's useful to write this general solution in a slightly different way. So let's call this psi sub e or psi sub e sub k. Well, let me just write it as psi sub e just to make it easier on myself. But now, remember, you can write e to the ikx as cosine ikx plus I sine cosine of kx plus I sine kx, and similarly e to the minus ikx. So you can express each of these in terms of sines and cosines, and so we'll write it in terms of sines and cosines instead as c sine kx plus d cosine kx. And so now what we want to do is impose our boundary conditions to figure out c and d. Okay, let's do that. Let's try to remember this. So our solution is of the form psi sub e of x is c times sine kx plus d times cosine kx. And this is a solution whose energy E sub k is h bar squared k squared over 2m. Okay, so now let's go ahead and impose our boundary conditions. So the first boundary condition says psi of 0 equal to 0. But when we have psi of 0, when we substitute x equal to 0, we get 0 equal to d times 1, because sine of 0 is 0. So this implies that d equal to 0. So all we have to worry about now is the sine part of the solution. Okay, so now we impose the second boundary condition, which says that psi of L equal to 0. So what this tells us is that c times sine of k times L equal to 0. And what this tells us is that k times L must be a multiple of pi. So it must be n times pi, where n is an integer. And therefore k must be quantized. K, just let's emphasize this fact by calling it k sub n. It can only take values of the form n times pi over L. So it takes only one of these discretely many values. K cannot be an arbitrary number. And in turn, what this means is that the energies are also quantized. So the energies are quantized to be E sub n is h bar squared k sub n squared over 2m. And substituting this, it's h bar squared n squared pi squared over 2m L squared. Okay, so the energy is quantized and must come from one of these discrete set of values. Okay, so now we can ask, well, are we done now? And the answer is not quite, because we also have to normalize. We must normalize our wave function. And so that's going to determine what C looks like. Okay, so now let's let psi sub n of x be equal to C times sine of KL. Well, KL is sine kx, which is n pi over L times x. And so the normalization we want is that the integral from 0 to L of psi n of x dx, so the wave function is non-zero between 0 and L, So the integral of psi n of x magnitude squared must be equal to 1. And this tells us that integral 0 to L of c squared times sine squared n pi over L times x dx, this is equal to 1. Okay, so how do we solve this? Well, you notice that the integral of sine squared over this period is the same as the integral of cosine squared. And so what this tells you is that 2 is equal to the integral of from 0 to L of c squared times sine squared plus cosine squared, the same quantity dx, and that's 1. And so that means that 2 is equal to c squared L, which tells us that c is equal to square root of 2 over L. Okay, so now this finally gives us our solution. So our solution looks like this. The proper set of eigenfunctions and eigenvalues of the Hamiltonian, it's indexed by n going from 1 through 1, 2, and so on. And the eigenfunctions look like psi sub n of x, which is square root 2 over L, sine of n pi over L times x, and the energy E sub n of this eigenfunction is h bar squared n squared pi squared over 2mL squared. Right? So the energy, as you go through the different values of n, the energy goes as 1, 4, 9, etc., etc. Okay, so the higher energy states have more modes because the sine function oscillates more. Okay, so let's just try to see this. Well, what does this look like? So this is what our solution looks like, and here's what the first mode looks like. It's for n equal to 1, so it's square root 2 over L sine pi x over L, and that's what sine pi x over L looks like. When n equal to 2, you'll get sine 2 pi x over L, and so you get 2 modes. When n equal to 3, you get 3 modes, and so on. Okay, so that's our solution to Schrödinger's equation. Now, of course, you might want to know, well, suppose you start off with psi of 0 as some arbitrary wave function. How does this evolve in time? Well, the way it evolves is as follows. So in order to understand how it evolves, you first write down psi of 0 as in terms of the eigenfunctions of h. So you write it as summation n equal to 1 to infinity of alpha sub n psi sub n of x. And now psi of t is just going to be, well, each of these eigenfunctions, what Schrödinger's equation tells us is that it evolves as follows. Basically, all that happens is that it picks up a phase. There's a phase that precesses at a rate that depends upon the energy. The higher the energy, the faster the precession. So psi of t is just sum of alpha n e to the minus I e sub n t over h bar psi sub n of x. Okay, so what we said in the beginning of this lecture is that this very simple model of a particle in a box, or on this line segment, in 1D line segment, this is a very good model. It's a very simple model of a hydrogen atom, of the electron in a hydrogen atom. Now, to see how good it is, you can even make this analogy quantitative. So if you look at E2 minus E1, so the energy of the ground state and the energy of the first excited state. So let's call this delta E. Okay? So delta E in the hydrogen atom is roughly 10 electron volts. Whereas delta E for our particle in the box, so let me call it box, delta E sub B, is h bar squared pi squared over 2ml squared times 2 squared minus 1 squared times 3. Okay, so what we could do is we could see if we were to set this energy difference for the particle in the box to be 10 electron volts, as we know from the hydrogen atom, then we could ask, what is L? Right? This would give us the diameter of the hydrogen atom. So what we can do is substitute the values of h bar and m, which is the mass of the electron, and see what we come up with. And if you actually do this calculation, what you get is that L is about 3.4 angstroms, which is about 3.4 times 10 to the minus 10 meters, or 3.34 nanometers. What we know is the diameter of the hydrogen atom is about 1 angstrom. So basically, this very simple back-of-the-envelope calculation gives us an estimate for the diameter of the hydrogen atom, which is within a factor of 3 or 4 of the true value. Okay. Moreover, what it does is it gives us a qualitative understanding of the hydrogen atom, and it gives us an understanding of how this quantization of energy happens. And so in the next video we'll see we'll take our idea of implementing a qubit using the electron in a hydrogen atom and interpret it with this particle in the box.